Okay, this is a really good problem. It's from chapter 37, and it's number 44. And it's a good problem because it's really all physics, very little math here. And so let me kind of review the double slit. And so if I had a screen here that had an opening, and so the light was coming in, and then it went through these two openings and through one slit and then another. And then it gets projected onto the screen over here. Then we like to say that right down the middle, there would be constructive interference. And the reason for that is because whatever the distance is from this top slit to the screen, it's the same as the bottom slit to the screen. And so as they come in, at one moment they will, this one will be at a crest, but then so will that one. And a moment later, this one will be at a trough, but then so will that one. And so they will be in phase, and so you'll get constructive interference, and so what we say here is you get a maximum. But then as you go either up or down the screen, I'll just go up here for a moment, then the bottom slit, the light has to travel a little bit further than the top one. And so they're not what we would say in phase. And in fact, if you go far enough, then, and we call, say, this bottom one path number 2 and this top one path number 1, then R2 minus R1, which I'll call delta R for the extra path length, if that turns out to be a half a wavelength, then what happens is when, say, the top one is at a crest, this bottom one is at a trough, and they then cancel each other. So destructive interference. Or a little bit later, maybe this one's at a trough, but then this one would be at a crest because they differ by half a wavelength. And so you get what we would call a minimum. You get what would be a dark spot. And so if you were plotting the intensity on the screen right here at the center of the screen, you would get a lot of intensity. And then as you move away from the center, either up or down, eventually you're going to get to a point, as I kind of just described here, where you would get a destructive interference. And, same would be down below the central one. So we got what we call the central bright one and then a minimum. But then as you go even further, and again, doesn't matter whether you're going up or down the screen, so I'll just show up here. Again, you can see that the bottom slit, the light's got to travel a little bit further, so I'll call this delta R again. And so this path minus this path would be eventually a distance of a full wavelength. And that means then that if this one on the top is hitting at a crest, this one at the bottom is also hitting at a crest. And so they line up together and you get constructive interference. And so you get a bright spot again. And so it goes up to maximum. And so this is the Young's double slit. And so you need to understand that first before this problem even makes any sense. And so, why do we get this constructive and destructive interference? And so if you've kind of gone through the material, there is an equation that is worked out that basically is saying the path difference, this R2 minus R1, can be written as d sine theta, where d is the distance between the two slits, and then theta is the angle of the light either up or down away from the center. And so that's the extra path length that the bottom one has to travel compared to the top one. And of course, if there's an integer number of wavelengths, you would get your maximums. And so right here, we would call this m equal to 1. And what we mean by that m equal to 1 is then the path difference is one extra wavelength. And so when it gets bright again, we call this m equal to 2. And then, of course, the center one would be m equals to 0. And so, again, this m then is an indicator of the path difference between the two beams. And so being 0 down the center and then going up or down, we would have an m equal to 1, although sometimes we like to label it as a 1 and a negative 1, so 1 going up and negative 1 going down. But in terms of absolute value, it's just a 1 and then a 2 and then a 3. And so I guess this right here where it's a minimum, this would be 1.5 wavelengths between the two. And that's why you got destructive, because it's got that half wavelength part. And then this, of course, was only a half a wavelength apart, and then this goes to a minimum. This would be 2.5 wavelengths. Okay, so knowing that then, maybe I don't need another piece of paper yet. Let's go ahead and get to the problem here. And the problem is then this, that you have this screen, and then this would be down the center right here. And so the light coming in this one and the light coming in this one would travel the same distance. And if that's all there was, then it would be a maximum. It would be very, very bright there, because those two would travel the same distances. And so what we would say is, again, m equals to 0. The path difference is 0. And so just to maybe make up a number, maybe there's 6 million wavelengths here and 6 million here. And, of course, the difference between them is 0. And so that's why we label it as 0. And the wavelengths are pretty small, so there'll be millions of wavelengths here. But the difference between them is what we're, focusing on here in this Young's double slit. That's why you get the constructive and destructive. It's not the number of wavelengths, it's the difference between them. And that's why this is important, because as we read this problem, number 44, it says, in a Young's double slit experiment using light of wavelength lambda, okay, so we've got wavelength lambda coming into the double slit. It says here, a thin piece of plexiglass having an index of refraction of n covers one of the slits. And it wouldn't matter whether we put it inside or outside. I'm just going to highlight the slits here. But let me put a piece of plexiglass here. And then for a comparison, let me put the same physical space, but there's nothing there. And so this is this piece of plexiglass, which they said has an index of n. Let's see, how do they write it here? They say a piece of plexiglass having an index of n covers the slit. If the center point on the screen of the spot is shifted, the screen is a dark spot instead of a bright spot. What is the minimum thickness of the plexiglass? All right, so let me call T then the thickness of the plexiglass. But here's what makes it a good problem, because here's where the physics comes in. What you're saying is, without the piece of plexiglass, going back up to here, this would be right in the center, this would be bright. That's because the number of waves from here and the number of waves from here, whatever it is, say 6 million and 6 million, is a difference of 0. But we also know that the wavelength inside of some kind of material, in this case plexiglass, is reduced by this factor of n. So that goes back to chapter 25. So even though the physical length is the same, the number of wavelengths will no longer be the same. That's the key, because they're smaller in this small space than they were up there. So here's where the physics comes into play. Since there is a smaller number of wavelengths in here, we could get more in here than in here. And what they're saying here is this spot is no longer bright, but it has gone dark. And so to even understand that before we can work out the math is to say, well, why did it go dark? And it went dark here is because you crowded more into this physical space of thickness T compared to what it was before you put the plexiglass. In fact, you crowded them enough that this has turned from constructive to destructive. And so that must be an extra half wavelength in here. Or it could be 1.5, 2.5, 3.5. But the problem clearly says the minimum thickness. So with that in mind, this problem becomes, as I said, more of a conceptual problem and more of a physics problem than it does a math problem. But once you understand that, now we can hopefully translate that idea into an equation. And here's what it would say. It would say then that this right here would have, this space would have how many wavelengths? And so what I'll do is I will say take its thickness t and divide it by the wavelength in that plexiglass. That is what we mean by saying how many wavelengths would fit into this. This is a quotient problem. This is division. This is why you learn division back in 4th grade. You know, if you wanted to know how many of these little things fit into the big things, you divide it. Okay, so if I go, okay, how many of these little things fit into the big thing, I would do a quotient here. Now, since I'm comparing it to the one above it, because again, it's the difference between them. It's not just how many, but the difference between them. I might do this. This would be the thickness divided by lambda naught. And so that would be the wavelength in the free space. And so, again, back to the conceptual physics of it, we know this turned dark. And it turned dark because we had more waves in here than in here. And how many more? Well, since it's dark, it has to be a half, or 1.5, or 2.5, or 3.5 wavelengths more in here than in here. Now, again, since they say the plexiglass is a minimum, then this would be a half. So if I were to subtract these two, I'm supposed to get 1/2. And there's the math part of it. I'll get the picture out of the way, and now I can solve this math. But again, just to get to this spot, the math is actually very easy here at this point, but that was kind of that tougher part. This was why this works. So now if I continue on with the math, I could, you know, write this as thickness equals, and to get the wavelength in the plexiglass, it's lambda naught over n. And then if I do 2 steps here, I'll factor out a t, but I'll also invert this. And then here's the t, and then of course luckily there's a common denominator of lambda naught, and so this would be n minus 1. And then so finally I can get t by itself by moving the lambda naughts over to here, and then I've got a 2, and then I've got the n minus 1. And so that is the answer in terms of symbols. And they don't give us any numbers, so that's the end.